Welcome to our first lecture in this course on linear algebra. Now, the mathematical objects that we will use most often throughout this course are the matrix and the vector. Okay, so let's talk about what a matrix is first. So a matrix is an ordered two-dimensional arrangement of numbers. And so an M by N matrix has M rows and N columns. All right? And so normally we'll represent those using capital letters. So we might have something like this. A is equal to 1, 2, 3, 4, 5, 6. So this right here would be a 2 by 3 matrix, right? Because it has 2 rows and 3 columns. Now the particular elements of this matrix can be referenced by using the subscripts of the particular row and columns involved. So for this particular matrix, what we have are these values. We have A11, A12, A13, A21, A22, A23. All right? So the 1 is at A11, the 6 is at A23, and so forth. And note here that rows and columns begin at 1. Now, if you've ever programmed, there's many programming languages that would have something that you might call an array, and this is basically like that. Now, in some of those programming languages, the indices, which is what these are, the indices of the row and columns might begin at 0, depending on the language. But in math, the indices of the matrix elements always begin at 1. All right? We'll come back to vector in a moment after we talk some more about matrices. Now, there are lots of special types of matrices that will have particular names, and matrices of that type will then have particular properties. But before we see some of those, let's also talk about something, and that is the main diagonal of a matrix. So the main diagonal are these elements starting in the upper left-hand corner and working our way down. So if we think of each element in the matrix over here as having a row and a column index, right? I is the row, J is the column. Well, the main diagonal are those ones where I is equal to J. So that would be A11, A22, A33, and so forth. So here, 1 and 5, because this is the A11 element, the 5 is the A22 element, they form the main diagonal. If I had something like this, B is equal to 7, 8, 9, 10, 11, 12, then 7 and 11 form the main diagonal. Okay? Now, one of the matrices that we'll deal a lot with is something called a square matrix. And the name is basically what you would expect. The shape is square because we'll have that the M rows is equal to the M number of columns. And in fact, typically we'll then, because of this, we'll say it is an N by N matrix. Right? So something like this. A is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. So this in particular is a 3 by 3 matrix. This one right here was a 3 by 2 matrix. And if we're going back to the main diagonal is the 1, the 5, and the 9. Okay? So there's one special type. Now, if we continue on discussing square matrices, and this is the plural, matrices, of the square matrices, one of the particular types is something called a diagonal matrix. And don't confuse diagonal matrix with the main diagonal of a matrix. Okay? So what is a diagonal matrix? A diagonal matrix is something like this. So what do we notice about this? Well, we notice that what we call the off-diagonal terms, those that aren't on the main diagonal, are only zeros. That's what makes a diagonal matrix. Okay? So the off-diagonal terms are zeros. What does that say about the elements on the diagonal? Well, nothing really. So I could have had this. 1, 0, 0, 0, 4, 0, 0, 0, 0. There's a 0 right here, but it's still diagonal matrix because we're looking at this. These are all zeros. These are all zeros. We don't necessarily care what's on the diagonal itself, the main diagonal, excuse me. All right? Now, if the values below the main diagonal are only zeros, then we say the matrix is upper triangular. So something like this. We'll put right here. So there's the main diagonal. All the elements below the main diagonal are zeros. So this is upper triangular. So we have this 10, 0, 0, 11, 12, 0, 13, 14, 15. Notice here, now the elements above the main diagonal are zeros, so this is lower triangular. And just like when we talked about diagonal matrix, where like in this case we had a 0 right here, this says nothing about the other terms. It just says if the elements below the main diagonal, okay, are zeros, it's upper triangular. If they're above the main diagonal, that's lower triangular. Which means that a diagonal matrix is actually both, right? Because it has zeros below, so it's upper triangular, but it also has zeros above, so it's lower triangular. Okay? There's another special type of matrix called an identity matrix. All right? And we'll normally write it just as a capital I. Now, if we care about the particular shape and we want to stress what shape it is, then we'll write a subscript indicating the number of rows and columns because it's also a square matrix. So I3 looks like this. 1, 0, 0, 0, 1, 0, 0, 0, excuse me, sorry, that should be a 1. All right, so 1, 1, 1 on the diagonal. So what do we know about an identity matrix? Well, it's square. It's a diagonal matrix, which also means it has to be square, so it's kind of redundant. And the main diagonal consists of only ones. Only ones on the main diagonal. So what happens if I have like 1, 1, 3 right here? Well, then it's not an identity matrix. It's just a regular diagonal matrix. So this is an identity matrix. 1, 1, 1, and these zeros here and these zeros here. And of course, we have other shapes, right? We can have a 5 by 5, 1,000 by 1,000, a 2 by 2. As long as they're diagonal matrices with all main diagonal elements being ones, they're still identity matrices. So what makes this so special? Well, the identity matrix is to matrix arithmetic what the number 1 is to real number arithmetic. So what do I mean by that? Well, if we're talking about real numbers, it's like 13.8 minus 42, 0, and so forth, right? We know, because there's an axiom with the real numbers that says if I take a real number A, and we could write like this, A is an element of the real numbers. This is what we call blackboard R. A is an element of the real numbers. We know then that A times, and I'll use parentheses for multiplication, A times 1 is equal to A, and we know that 1 times A is equal to A, right? When we're talking about identity matrices, what we'll see, and we'll find out how to do some other things related to those later, but when we talk about matrix multiplication, we'll see that I times A equals A and A times I is equal to A. Now, it may not be the same I in both cases because the shape of the identity matrix may have to change. For example, this may be 3 by 3 and this may be 5 by 5. Okay, but nonetheless, some identity matrix, as long as it's legal to perform this product, will lead to A, and A times I, once again, as long as the shapes are such that this is a legal product, will also lead to A. Okay? Let's talk about vectors. Now, eventually we'll see a more formal definition of something called a vector space. But you may have already seen vectors before, at least in some form. Maybe if you took a physics class, for example. And what they may have shown you is they may have given you the XY plane. Right? Looks something like this. So here's the X values, here's the Y values. If we have 1, 2, 3, 1, 2. Then we would say this directed line segment here is a vector, and it has coordinates 3, 2. Okay? So how do we represent that as a vector in the linear algebraic sense? Well, the way I would write that, normally I would do something like this. So it's very common to use the letter X. But we want to distinguish between vectors and real numbers, or actually scalars. So a scalar is basically some number. 13.8 minus 42, 0. Complex numbers, but still a number. But a vector, I'm going to write like this. I'm going to put a little arrow above it. In a textbook, typically what they'll do is make it bold-faced, but I can't really do that, so I use the little arrow. And so to represent this vector right here, I'd write like that. So then that leads into the discussion of, is it okay to write it like this as opposed to this? My answer is, it depends. When we're not using the vector as part of a mathematical operation, and you're just talking about coordinates in space, then I'm perfectly fine with writing it in what we would call here a row vector, as opposed to a column vector. Right? Because this looks like a row, this looks like a column. I'm perfectly fine with this when we're just talking about dimensions in space. Right? But if you want to use it as part of a mathematical process, in the sense of what we're talking about here is, addition, subtraction, or multiplication, which are all defined for matrices, well, then if that's what you're doing, shape matters. And so unless specified otherwise, the default shape is as a column vector. Okay? So we'll even eventually talk about how a matrix, something like A, 1, 2, 3, 4, 5, 6, 7, 8, 9, can be thought of as consisting of 3 columns. There's a vector, there's a vector, there's a vector. Okay? And that will become important when we do certain things later, but we're not even close to being ready for that yet. Okay? So in our next video, we'll talk about the arithmetic of matrices, or matrix algebra, some people would say, okay, where we see these operations. And then we'll also see, or I'm just going to tell you now, division is not defined for matrices. So you never divide one matrix by another. But under the right circumstances, we can multiply 2 matrices, or a matrix and a vector, or add 2 matrices, or whatever. We just have to talk about a lot more details in terms of how you define these, which we'll do in a later video. But that's enough to get us started on what the idea of matrices and vectors are.